Ljudmilia Kamenova. She will talk about Kobayashi conjecture for K3 and hyperk.
Thank you for the invitation. I will consider compact hyperk manifolds. I'm going to use the algebraic definition most of the time. So this is a compact complex Keller manifold, which is simply connected. And such that H foot 0, 10 is one-dimensional, and it is generated by everywhere non-degenerate holomorphic two-form. So this definition is equivalent to the differential geometric definition, which says that the Stony group is SPN. This is the compact subjective group. So unlike in the non-compact case, where you consider compact hyperkellers, there are so many examples. For example, the standard examples are K3 surfaces. These are all the examples in complex dimension 2. And then you have higher analogs of K3 surfaces. For example, you can have the end of S, where S is a K3 surface. You can also have generalized Kummer varieties, K and of A, where A is an abelian surface. This is constructed in a very similar way as the Hilbert scheme. So the way you construct the Hilbert scheme is you just singularize the symmetric product of S plus S n times, modulo the action of the symmetric n group. So for this construction, which is called the generalized Kummer variety, you do something very similar. So instead of Hilbert of A, you can take Hilbert n plus 1 of A. And again, this is the singularization of A plus A, n plus 1 times, modulo the action of S n plus 1. And now, because A is an abelian surface, you can sum up those n plus 1 points and take an image to A. So the problem with Hilbert n plus 1 of A is that it is not simply connected. And also, there are too many holomorphic two forms. The way to solve this problem is to take some distinguished point on the abelian surface, let's say the 0 point, and then take the image of the 0 point and call this Pn of A. So these are the standard two examples of high-dimensional hyperkeller manifolds. They're due to Bouville. And when n is 2, this example was due to Fujiki. So other than this two infinite series of examples, there are two more exceptional examples due to Grady. I call them O1 and O2. These come as desingularizations of moduli spaces of semi-stable sheaves, which are not stable. But the construction is quite involved, so I'm not going to discuss it. And other than these examples, you have deformations of such examples. And so far, these are all of the known compact hyperkellers.
What dimensions are the Grady examples? examples again?
Complex dimension 6 and complex dimension 10. So the interesting thing about these examples is that they all admit Lagrangian vibrations. So let me say a few words about Lagrangian vibrations.
Also, the deformation admits those?
Okay, so for each one example, there exists a deformation which admits Lagrangian vibration. So I'm just considering examples up to deformation equivalence. So let me state a theorem by Matsushita. Which says the following: if you have vibration structure on a hyperk manifold, so this is the proper surjective map from a hyperk manifold to a base P. So proper surjective with connected fibers. Then necessarily the dimension of the base is half of the dimension of M. And the general fiber.
So F is just a smooth map?
Oh yes, just a smooth map with connected fibers. Then the general fiber F is an abelian variety. Also half of the dimension, and moreover it is Lagrangian.
It can be deformed over to Lagrangian, or?
No, the abelian variety is Lagrangian with respect to the holomorphic form of sigma here. So sigma.
If F is just a smooth map, you can perturb the map, and so but you're saying you can perturb, you can homotop it to Lagrangian.
Well, so in this map, it is smooth in the algebraic category. However, the fibers themselves can be singular.
Is F a holomorphic map? You said
Yes.
That's what I was asking when I said, is it just smooth?
Yeah.
It's a holomorphic map, and
That's
it's also supposed to be a smooth.
Yes.
Well, maybe. Okay. Holomorphic map.
It's a holomorphic map. So you have some smooth fibers, some singular fibers, and so on. All of the smooth fibers are abelian varieties, and then the singular varieties, if they have a smooth component, it is also an abelian variety, which is Lagrangian with respect to sigma. So sigma is restricted Okay, so the base a priori could be singular. However, if you assume that the base is smooth, you have the following theorem by Brook. So if it is smooth, then it is isomorphic to CPN. And in all of the known examples, whenever they have a vibration structure, the base is smooth, and indeed it is CPN. So in general, you can just think of when you have a vibration, this is the vibration from M to the complex projective space, and then the general fiber F is smooth, which is an abelian variety, and then you can have a whole device of fibers, but their smooth components are Lagrangian. Okay, so given compact because for this talk, all of the hyperkillers will be compact. So given a hyperkiller manifold, there exists a special form on the second homology. So there exists revealed homology intuitive form on the second homology of N, which is integral primitive form. It actually generalizes the intersection pairing for K3 surfaces. So it is a signature 3 B2 minus 3. So unlike the intersection pairing for K3 surfaces, this intersection pairing is not unimodular.
So you use sigma wedge sigma bar to a power to promote?
Yes, that's right. So this is the way to specify the form is using the Fujiki relation, because instead of defining it with integral of sigma bar to some powers and so on, the Fujiki relation is quite compact and it is very useful. So if you have a class in H2 alpha, when you take alpha to the 2n over n, so this is some positive constant c depending on the topological type of the hyperkiller times q of alpha to the n. So alpha is in here. Okay, so using this form, I make the following trivial observation. So if you have a vibration from n, and now from now on I will assume that B is smooth, so it's Pn, Cpn. So if you take an n-well class on the projective space, for example, you can take a hyperplane class here, and then pull it back to n. Let's say alpha is f upper star of h. Then this class alpha is net with conjecture model form with range. So how do you see this? The way you see it is if you take a hyperplane in CPN and start intersecting general hyperplanes, then after you do this n times, you get a point. And then if you intersect n plus 1 times, it will be the intersection of a general point with a general hyperplane, which will be 0. So then you have that h to the n plus 1 is 0. Therefore, alpha to n plus 1 is also 0, so this part is 0. C is a positive constant, and therefore the Bogomolov form not vanish. So this is one good property of the Bogomolov form, that whenever you have a vibration, you produce...
So Q of alpha denotes Q of alpha alpha, so you're taking the bilinear.
Q of alpha alpha, yeah. So whenever you have a vibration, you see this using this integral form from the second homology. So it's very similar to K3 surfaces because with K3 surfaces it's the same. If you have net divisor with square 0, then it gives you a vibration. And here, this is the SYZ conjecture. The opposite direction also holds. So if you have L, which is net line bundle, conformations of L give a vibration structure on M as above. So L gives a vibration. So this conjecture, the SYZ conjecture, so far has been proven for some of the examples. So if you have Hilbert scheme of K3 surface.
When you call this the SYZ conjecture, it's just by analogy to the usual SYZ conjecture in mirror symmetry. It's not literally, they didn't have anything to do with this conjecture, did they?
That's right, it is by analogy. This conjecture was proven for the formations of Hilbert schemes of K3 surfaces independently by E.L. Markman and Bayer and McCree in 2013. And then for the generalized Kume varieties, Kn of A, it was proved by Yoshioka in 2012. So already we know that the SYZ conjecture is true for most of the examples.
So that's true for all deformations or just?
For all deformations, yes.
And this is a vibration to something, not to Pn apart, just to.
It have to be exactly.
It has to be Pn. Yeah, because
and n is half the dimension.
Yes.
So there must be an index statement that you, in particular, that you know that this implies that L has. Oh, but then you could take the power of L. So.
Well, you can have different vibrations, but they're all be to CPM. You can vary the fibers, vary the map. So.
I guess, I mean, in terms of the way that it gives rise to the vibration, all I'm saying is that the way it's set up, you could take a root of L. I mean, if L satisfies these hypotheses, so does L to the K for any K.
That's right.
So it's actually asserting that L has some root, which has exactly n+1 sections and defines the linear system, defines a map to Pn. Is that right?
Yes, that's right.
Yeah, sorry.
Amazing.
What if L is trivial?
It has to be non-trivial.
It's Neff by assumption.
It's in the boundary of the Keller cone, but it's different than zero.
Okay.
Yeah, so for the trivial line, although it doesn't work.
It's not big enough for anything. It's not some X-ray box.
Obviously not.
Right.
So if it's big, then Q of alpha will be different than zero.
That's too positive.
Yeah, that's right.
It's just, I was concerned about the possible, yeah. How big was zero exactly? That would be the math, unless you make some extra.
Okay, so I mentioned the SYZ conjecture because we'll need it a little bit later. Now, let's go back to the title of the talk and let me introduce the Kobayashi pseudometric. So, if you have any compact complex manifold M, then you can introduce the Kobayashi pseudometric. It is denoted by Bn. So I'm going to introduce it using one of its properties, which is the following. So this is the maximal pseudometric such that every homomorphic map from the unit disk in the parametric to M with this pseudometric is distance decreasing. So if you consider all metrics with this property holomorphic map from the unit disk to them is distance decreasing. And then you take the supremum, then you obtain a Kobayashi pseudometric.
So pseudometric here means any Fensler metric, or?
So it satisfies, it is non-negative, satisfies the triangle inequality. However, it's possible the distance between two different points to be 0. So it's a metric which measures the distance between points on M. The way Kobayashi originally defined it was using Kobayashi chains disks. So basically what he did was, if you have 2 points x and y on your manifold M, you can cover them by chains unit disks, and then measure the distance between this point and then the point of the intersection, and so on. Then sum up all of these distances and take the infimum between all the chains of all such with such property. But we don't need the definition.
It also has a Fensler type definition, right? You can actually define what you mean by the length of the tangent vector.
That's right. You can also define the infinitesimal version of the Kobayashi pseudometry on the function space. But for our purposes, we just need a simple metric which measures distance between points.
Sorry, what's capital D here?
That's
So
the
the
unit disk in the
system
complex line, right?
Yes.
Basically asking how large a complex disk can fit in manifold.
That's right.
You can always get a complex disk and a complex manifold, but you hope you can't get a complex line.
Yeah.
Then it becomes degenerate if you can actually find a map of C. So it's sort of the maximum size of a disk with a given tangent vector.
Okay, so if this is a metric, so which means that if the distance between different points is non-zero, then the manifold is called Kobayashi hyperbolic. And if this is not a metric, but it is a true pseudometric, the manifold is called Kobayashi non-hyperbolic. And as Paul was mentioning, we have the following result by Brody. So I'll state those results. The first one is that they both work for compact complex manifolds, the way we are set up today. So N is Kobayashi non-hyperbolic. If and only there exists an entire curve on M, which is a holomorphic map from C up to M. So if you have disks with big radius, infinity big radius mapping to M, then it has to be Kobayashi hyperbolic. So such entire curves on M basically were studied by Kobayashi first, and that's why he introduced the pseudometric. Because with this pseudometric, you can measure what kind of curves you can have on your manifold. If you have a rational curve, or singular rational curve, or elliptic curve, or some singular elliptic curve, then this metric vanishes in some direction. So this is one way to establish when your manifold has certain types of curves. Or if it has an abelian subvariety, then you can also sketch this using the pseudometric. And then the second interesting property that Brody established is that non-hyperbolicity is preserved in the limit. moduli space of complex structures, and you have points which limit to a certain point in this moduli space. If all of the points are non-hyperbolic, then the limit is also non-hyperbolic.
So this is without any assumption that the bad directions converge in any way. I mean, it's like they could be popping up all
They
of them.
can be anywhere. For example, all of the bad directions can be one way, and then in the limit it can go to a different direction. That's possible.
So as soon as you have like a statement that a dense set in the moduli space contains rational curves or something, that like you guarantee that it's not hyperbolic.
That's right.
So it's an entire curve, that's just a holomorphic injection of the
Non-trivial holomorphic map.
non-trivial.
Just non-trivial.
Yeah, it can have singularities.
It could be a map of, it could be an elliptic curve, for example.
Right.
Yeah.
Thanks.
And regular hyperbolicity is not necessarily preserved in the limit. However, non-hyperbolicity is preserved.
What's regular hyperbolic?
If you have a sequence of Kobayashi hyperbolic manifolds, then the limit may or may not be a Kobayashi hyperbolic. Okay, so now we're ready to state Kobayashi's conjectures. The first conjecture, which has been open for a long time, he made them 4 decades ago. Is that if S is a K-free surface, then the Kobayashi pseudometric on S vanishes identity. And then he asked if something similar is true in higher dimensions, if you have a Calabi-Yau or hyperk manifold. So I'll state them in some order. The second conjecture is that if M is a hyperk manifold, meaning compact hyperk, then the Kobayashi pseudometric also vanishes. And you can ask a weaker question, so I'll say this as 2 prime. So if M is hyperk manifold, you can ask a weaker question, is it or is it not Kobayashi hyperbolic? Of course, the expectation was that M is Kobayashi non-hyperbolic. I'll give a little bit of history about the progress on these conjectures.
So this is S. Kobayashi, the one at Berkeley?
The one, yes, S. Kobayashi. A lot of people have worked on these conjectures. For example, Claire Boissin, Lang, Campanam, many others, Serge Campau. So what we have so far is the following. Using Mori-Mutax results from, let's say, 82. You can see that all projective gateway surfaces are swept out by singular elliptic curves. Sometimes they're non-singular, but in general, every projective gateway surface is covered by singular elliptic curves. So, using this fact, you can see that conjecture 1 is true. metric KQ surfaces. And for a while, it was open for non-projective K3 surfaces. Then in 92,
So that immediately gives all of the K3 surfaces are Kobayashi hyperbolic, therefore, because these are dense, right? And
no. That's right. So all K3 surfaces are Kobayashi non-hyperbolic. That's what it gives you, but it doesn't give you that
the distance is zero.
is zero. That's right. That's correct. Then Kamenova made some progress in terms of hyperk manifolds using twistor spaces. So the way twistor spaces are presented in hyperk geometry is the following. Since you have the determinants acting as parallel homomorphisms, you can fix the basis I, J, K of each. And if you have lambda complex structure in this basis, then you have that x squared is negative 1, if and only a squared plus b squared plus c squared is 1. So ABC lies on S2, or I'll think of it as CP1. So the way people think about twistor spaces in hyperk geometry is, let's call it Z. Depends on the metric. This is the family of complex structures compatible with a given metric. So this is has a homomorphic projection to this sphere CP1. So this line is actually homomorphic, so this is nice. And also this CP1 gives you a line inside of the deformation space of your hyperk manifold. So this is a local line. So anyway, Kamenova proved that for every metric G, there exists at least one fiber
many people do this, so the fibers of P1, so looking at it backwards, so sideways, so it's
That's
there's
right.
one complex structure in that family. There's one lambda.
There exists
One lambda.
lambda in P1, such that the fiber which is M with G and lambda is Kobayashi non-hyperbolic.
So this is for just an arbitrary compact hyperk.
Yes.
The idea is you take a twister fiber, you bend and break, so it eventually,
That's right.
you move it until it becomes horizontal.
Okay, so until recently, this was the latest general result. Then in 2012, together with Verbitsky, we used the density of Lagrangian vibrations inside of the moduli space of hyperk to prove that all autonomous hyperk examples are Kobayashi non-hyperbolic. Then the following here, we show this scheme. conjecture 2 prime is indeed true. So prove conjecture 2 prime.
So this doesn't involve any classification.
No, it doesn't. As soon as so in 2 minutes, I will tell you the method. Okay. So suppose conjecture 2 prime is weaker. It just says that Kobayashi pseudometric vanishes in some direction. However, we want something stronger, namely whole vanishing, that it vanishes in all directions. So in 2013, together with Stephen Brook and Misha we prove the following theorems. So we completely settle Kobayashi's conjecture for K3 surfaces. If S is any K3 surface, then the S is identically 0. Now, if you have a compact hyperk manifold M, you can consider, let's consider 2 cases. The first one is when the pk rank is less than maximal, because H2 decomposes as H20, which is one-dimensional, plus H11 plus H02, which is also one-dimensional. The maximal possible pk rank is P2 minus 2. So under this assumption, also assume that M is the formation equivalent to Lagrangian vibration, which of course all of the known examples are the formation equivalent to Lagrangian vibration, and it is conjectured that in general this is also true, so hopefully eventually we'll be able to drop this assumption. Then the pseudometric vanishes identically. And now the question is, what happens when the pk rank is maximal? So if M is hyperk manifold, we draw which is maximal. So it is beta minus 2. Then you have to make a stronger assumption. You have to assume the SYZ conjecture on all deformations of M. And then the same result will follow that the M is identically 0.
So the SYZ conjecture before, I thought it was about deformations of the thing, but you're saying assume that every single one has such a line bundle? Or?
So the SYZ conjecture was the following. If you have L, which is an F line bundle, such that P of L is 0, then this L
Oh, I see.
gives you a vibration of the manifold.
I see. So the problem is you're in a setting where there are lots of line bundles. Yeah, the other case where you can get a better result than the one where there are few line bundles.
That's right. And because that's why the conjecture is already settled for deformations of Hilbert schemes and deformations of the generalized Kummer, as a corollary, for them we can drop all of the assumptions because you can combine both theorems together, and you see that the n incident is zero. If n is the deformation of Hilbert scheme on a K3 surface, or a deformation of the generalized Kummer graph.
So the O'Grady examples are currently harder than.
Yes, currently for them we don't have the XYZ conjecture. They are slightly less studied. Recently they've been studied by some students of O'Grady. And you can say a lot about their invariants and such, but in general they're more difficult cases.
So that corollary, that's unconditional because we know the SYZ.
That's right. Yeah. And also we know that each one of them is information equivalent to one that admits Lagrangian vibration. But we know that's YZ which is stronger. Okay, so now in the remaining time I'll give you some ideas on how to prove these theorems. So what we'll do is we'll consider the Stony space, which is a higher dimensional analog of the Stony space on K3 surfaces. Kamenova was studying it for compact complex manifolds. And the way you can define it is the set of complex structures, modulo connected component of the diffeomorphism group of M. In general, it can be infinite dimensional. However, if you have a Kobayashi or hyperk ahler, it is finite dimensional. However, it is highly non-Hausdorff. You can have a lot of non-separated points. However, non-Hausdorff spaces are not very difficult to deal with.
So the infinite dimensionality would be saying that you could have jumping of complex structures to the H1 of the tangent bundle if it's very large someplace.
Yes.
So if you don't have bounded size, it's not that it's sort of locally, it's locally finite dimensional, but it could have straight up bigger and bigger.
That's right. But for hyperk ahlers, we don't have to worry about this. It is finite dimensional. And also, analogous to K3 surfaces, we have an action of the mapping class group here. So you can define the mapping class group as traditionally as, let's say, the orientable diffeomorphisms of M. Modulo, again, you have a connecting component. And there is a natural action of gamma on the Teichmüller space. So I'm going to define what is ergodic action. So if you take a complex structure I in the Teichmüller space, this complex structure is called ergodic. If the orbit gamma times I is dense in the Teichmüller space. So the motivation behind the ergodic action is the same as the regular Because for hyperk manifolds we have global threading. So there is a period map from a time space to the period domain, which is a quotient of two non-compact Lie groups. And there you have the harm measure, and you indeed have ergodicity of the action of gamma on this quotient of non-compact Lie groups. So that's why we call such a structure ergodic. Okay, so actually the orbit gamma of I can be written as complex structures I prime in the finite space, such that I together with I is biholomorphic to M together with I prime. Okay, so for hyperk manifolds, there is a classification when complex structure is ergodic. So I is ergodic if and only if the decay rank of M together with I is less than maximal. So as usual, we have that the orbits of points which are non-ergodic has measure 0. But from this theorem, you see that something even more is true. If you have a non-ergodic orbit, then such complex structures are only countably many. Because when the current is maximal, this is basically intersections of hyperplane of codimension 1 spaces in lattices. So at the end, you end up with countably many intersections. So there are only countably many ones which are non-ergodic. So let me prove one key proposition. If you take a complex manifold M with J, such that Kobayashi supermetric vanishes, and if you assume that I is ergodic complex structure, in the same deformation class as J, then you also have the Kobayashi pseudo-distance of M together with I also vanishes. This computation is based on the fact that if you take the diameter function from the bipolar space to R non-negative, so the idea is the following. This function is upper semi-continuous. Which means that if you have a sequence of points inside of a bipolar space, then if there are limit points, it can only jump or stay the same. So in particular, if you have an ergodic complex structure in a bipolar space, then it's everywhere dense. And then J, which is a limiting point, in the limit, it can only jump, but because it's already 0 in the limit, for the ergodic complex structure, it also has to be 0. So this is the idea of the proof. sketch how to prove the first theorem. So if you have a gateway surface, well, let's consider the following two cases. So in the first case, let's take the theta rank to be maximal. So in this case, the rational 1-1 classes are dense in H11 of this, which means that there exists a rational 1-1 class inside of the Keller cone. Well, by Kobayashi, this means that this is projective. And for projective gateway surfaces, we already know that the Kobayashi pseudometric is 0. So then the second case is what happens if rho is less than maximum. By this classification, rho is less than maximal if and only if the complex structure is ergodic. So this is equivalent to the given complex structure Si being ergodic. Well, any two gateway surfaces are deformation equivalent to each other. So what we can do is deform S together with I to a projective gateway surface. So deform to a projective gateway surface S with a complex structure J. And now, for the first case, we already have that the S trace vanishes, and we are exactly in the setting of the key proposition. So you have an ergodic complex structure, deformation equivalent to a structure with vanishing Kobayashi pseudo distance. And then for the proposition, we also have that ds with the given ergodic structure vanishes. So that's how you get the theorem for gateway surfaces.
So let's see, in the projective case, you've got all of these elliptic curves on the surface, but you're actually saying they point in sort of generic directions, not just in a vibration or something?
It is swept out by different families in different directions. So you have lots of singular elliptic curves, which not go only in one direction, but they also go in different directions. And the key is, if you have any two points, you have them lying, or let's say you take one singular elliptic curve in one direction, and then another singular elliptic curve in another direction. And then the distance from here to the intersection point is 0, because it's elliptic curve. Then here it's also 0. But then by the triangle inequality, the distance between this and this is also 0. That's how you do it for projective K3 surfaces. And in the general case, if you have hyperk-ahlers, I just have to find, to give you the idea of the proof. What you do is, if you assume that you have two Lagrangian vibrations on n, so n to 1, to distinguish them, let's call them base 1 and base 2. So di, these are the two projections. So if you have two distinct Lagrangian vibrations corresponding to two non-proportional classes, then the idea is the same thing. You can do some intersection theory and prove that the general fiber F1 of the first vibration intersects the general fiber F2 of the second vibration. And then with the same kind of thinking, you see that the Kobayashi pseudo-distance vanishes on n. And now, how to resolve the second theorem? Basically, inside of the Ljudmilia space, you have the divisor of which parameterizes Lagrangian vibrations. It is the divisor because it is basically determined by Q of L is 0. And then this divisor self-intersects. And you can choose, using the mapping class Brook, intersection such that the two directions are transversal to each other. And then on this intersection, you're going to have a double Lagrangian vibration. So from this observation, on the double Lagrangian vibration, the pseudometric will be 0. And then, again, you can use the key proposition to say that because the complex structure is with is ergodic, then it is the formation equivalent to this one with a double vibration which vanishes. Therefore, it also vanishes. So this is the basic idea of the proof. Of course, it is more technical, but this is the underlying geometric proof. Now I'll stop here.
Could you say something about how does Verbitsky prove this statement about ergodicity? It sort of seems like one of the main machines you need. That,
So in order to define ergodicity, he uses some results of Galvin-Moore about ergodic actions of portions of non-compact E groups. And then Marina Ratner had some results by herself about closures of orbits. And then he uses her results in order to do this proposition, how to characterize ergodicity in terms of the maximality of the Picard rank.
I mean, you need some kind of Torelli theorem to set this up?
Yes, you need Torelli. Yes, because the Ljudmilia space, if you take a connected component, it basically looks like SO3 B2 minus 2 modulo SO2 times SO1 B2 minus 3. And then instead of working with the Ljudmilia space, you start working with the period domain.
There's some subtle failure of Torelli in higher dimensions. I'm trying to remember if you have to state it exactly correctly.
Oh, that's a very good question. So the way it's stated for K3 surfaces, it is using Horsch theory. But for K3 surfaces, since they're surfaces, the Horsch theoretic interpretation is the same as the interpretation with complex structures. And then in higher dimensions, you just have to do it to set it up right. Because if you use Horst structures, there are many counterexamples, but the right way is to use the Ljudmilia space of complex structures. Otherwise, if you use Horst structures, there are many failures. And for K3 surfaces, they're the same, and people were trying to generalize it for years using the wrong setup.
But it's actually done in terms of the span of IJK, is that right? It's the right point of view?
Well, a little bit more complicated in terms of the Ljudmilia space. Yeah.
Any more questions?
So you can prove this